everyone. Welcome to my talk, the AWS SDK for Kotlin. I'm Ian Botsford. Let's go ahead and get started. So what we're going to talk about today is a little bit of introduction to AWS, to SDKs, and the AWS SDK for Kotlin. We're going to do some live coding demos. Hopefully everything works out well there. It's always a bit of a risk. And then we'll talk a little bit about some future plans and some next steps for the AWS SDK for Kotlin. So to start with, how many of you have played around with AWS before? Show of hands. Okay, most people. That's good. So then much of this will be review or refresher for you. Amazon Web Services consists of over 300 different web services, everything from foundational components like S3 for storage, Lambda for compute, to building blocks like DynamoDB for big data or SageMaker for machine learning, all the way down to very specialized services like RoboMaker for robotics, GameSparks for gaming, etc. Developers typically access AWS in one of 4 different ways. There's the AWS console, an interactive website for viewing and managing your AWS resources. There's a command line tool that's useful in scripting scenarios. There's occasionally, hopefully very rarely, raw HTTP requests that you could write yourself and send to AWS services and then parse the raw HTTP responses. But by and large, the most popular and the most preferred way for accessing AWS by developers is by an AWS SDK. So before I get into what makes an AWS SDK, by show of hands, who here has used an AWS SDK before in any language? Okay, all right. Slightly less, but still quite a few. The software development kits for AWS services are clients for individual AWS services that are written in languages that developers need to code in. There's an AWS SDK for Java, for Python, the Kotlin one we're going to talk about today. All told, there's 12 different languages that AWS has SDKs for. Each of these SDKs have over 13,000 operations in them, or APIs, methods that you can invoke against a service to perform some sort of action. Between the inputs and outputs and all the different types of data that those operations need, there's over 136,000 shapes in each of the AWS SDKs. These shapes are things like structures, fields, enumerations, other kinds of data that are necessary to kind of marshal data back and forth between your code and AWS. All that is to say that the surface area for an AWS SDK is huge, and we don't handwrite most of the code that goes into them. Instead, we code generate the SDKs from Smithy models. Smithy is a service description framework and a set of code generation tools developed by AWS, open source and publicly available, that are used to describe each AWS service, each operation it supports, what kind of data it uses, so on and so forth, so that we can maintain large SDKs with relatively small teams. For example, the Kotlin SDK consists of about 76,000 lines of handwritten code, runtime handwritten code, and then about 6 million lines of generated code. All right, last question. Who here has used the AWS SDK for Kotlin before? A couple people. All right, well, so then most of this will be new to you then. The SDK for Kotlin is a brand new SDK written entirely from scratch. It's not based on the AWS SDK for Java, which is what a lot of people seem to assume when they first hear about it. Instead, it was written from the ground up to be Kotlin idiomatic. It makes use of Kotlin syntax and Kotlin conventions like DSLs that we hope will be familiar to Kotlin developers. It uses the best Kotlin types and null safety from the Kotlin types system and the standard library to strongly model data as well as possible. It's built to be ready for multi-platform. It supports JVM on the desktop and on Android today, but we hope to be adding support for more platforms soon. And then it's got support for coroutines built in. Every operation that you can invoke against an AWS service is a suspend call, which sets it up nicely to play with Kotlin's cooperative multitasking. Okay, now that I've got the intro out of the way, we're going to switch to some live coding. Cross your fingers that nothing goes wrong, or that it goes so horribly wrong that it's hilarious. All right. First thing we need to do is actually add some AWS service clients to our dependencies list in our Gradle configuration. Each AWS service has its own dependency, its own library that can be pulled in separately. This is important because, as I mentioned, those 6 million lines of code compile to actually quite a large set of binaries, and we don't want to necessarily include every AWS service client in your code if it's not necessary. So by adding one or more dependencies on specific services, we can keep deployment sizes small for your end application. All right, I've got my 2 dependencies added. Let me just pop open the Gradle tab and refresh my Gradle configuration. And now the IDE should be set up to do autocomplete and so forth with my dependencies. All right, so let's start with a quick hello world example. We'll add a main function here. We'll create a service client, in this case a client for S3. I'll talk about each of these lines in a little bit more detail in just a second, but for right now, we'll set up a response to come from a particular S3 operation. And then we'll print out the response, or at least the interesting parts of the response in the console. Oops. All right. If I did everything correctly, we should see a couple of objects being printed out on the screen. Eventually. Well, these weren't the objects that I had wanted to show, but that's because I am looking at the wrong bucket. If I update my bucket to the one that I wanted to show originally, I'll see a much shorter list of objects. There we go. The objects hello and world. So I said I'd take a look at these lines in a bit more depth here, and that's what I'm going to do now. The first thing we need to do is to get an instance of an actual service client, in this case S3. The easiest way to do that is usually calling the from environment static extension method on the S3 client class. This inspects the local environment on the host machine and tries to find the configuration parameters necessary to connect with AWS. Things like credentials, other configuration, specialized endpoints, anything that might be necessary to communicate with AWS. There are ways of explicitly passing this configuration, but most often, if you already have profile files configured for other SDKs or for other AWS use cases, simply finding things in the environment is the fastest and easiest way to get your code up and running with AWS. Next is an actual operation invocation. So the list objects v2 API is an operation that lists all of the objects that it can find in a particular bucket. In this case, I have to give it the name of the bucket, and I do that by passing it in a lambda to the list objects v2 operation. Last, the response that comes back contains a contents array, and for each of those contents, I print out something interesting about the contents, in this case, the key or the name of the object. Let's go a little bit more in depth about ways of making different kinds of calls to AWS services. So the simplest way is the way that we just saw on the previous example. We call some operation like list objects v2. We give it a couple of parameters. And we give it a run. Oops, that was too fast. Didn't catch the syntax error there. All right, so this bucket I'm looking at has many different files in it, well over 100. So I may want to pass additional parameters to this API call that limit the number of responses that I get, say to 10. I may want to add a prefix to the search so that it only returns files beginning with the letter C. Every different parameter that I can pass to an operation in this DSL syntax is a value assignment. This is one way of calling AWS services, and it's generally the simplest way, and so it's the way that we favor in most of our documentation and most of our examples online, but it's not the most flexible way. A more flexible way of calling AWS services is by creating request objects. So the request objects take the same parameters as the direct DSL invocation on the method itself. But because they're objects that can be passed to an operation by reference, that means that we can reuse the objects in our code multiple times. If we have a single request object that we pass around to different points of the code that call the list objects v2 in different areas, it's way easier than duplicating that DSL syntax everywhere we need it. I intended this to be a different result than the first result, but there we go. Another advantage of request objects is that you can copy them and modify only certain parameters about them, thus using a request object kind of like a template. So I'm not going to invoke another operation on that, but you can get the idea that request objects are a bit more flexible in the ways that you can use them to call AWS services. One kind of request that requires a little bit of special attention are requests that involve sending byte streams. Byte streams are unstructured, arbitrarily large arrays of binary data, and we have a special data type in the AWS SDK for handling those. One of the cases where you might need a byte stream is actually uploading an object to S3. So the body parameter of the put object operation is the one that takes the binary stream, or the byte stream. Byte streams can be derived from files in the local file system, from strings in memory, from byte arrays that are in memory. And moreover, the byte stream class itself is abstract, so you can write your own implementations that adapt JVM input and output streams, reactive streams, or any other kind of streaming data source that you may have. In this case, I'm going to use a file from the disk. All right, let's run that. Okay, cool, my object was uploaded. Now the very next thing I might want to do or demo is show downloading an object, and that's the last kind of way that you can call AWS services. That's when you're expecting a byte stream response. When you're expecting a byte stream response, you have to use request objects to make an operation call. So in this case, I'll create a get object request. For my file. And then pass it to the get object operation. Operations that return a streaming byte response need to have a lambda for handling the response. That's because the response has a well-defined lifetime and will be cleaned up and garbage collected after this lambda is over. We do that to make sure that these large streams of data definitely get closed and definitely get deallocated so they don't cause memory leaks in the application. Inside this lambda, I've got full access to all the properties on the response, such as, in this case, content length. And I can perform operations on the streaming body itself, such as writing it out to a file. Let's give that a run. Cool. So my object was successfully downloaded, and I've now shown kind of the 4 main ways of making requests to AWS services. Just one final note, a little bit about package and namespace organization. The S3 client that I've been using is defined in kind of a top-level, well, not quite top-level, but a high-level AWS S3 namespace. The DSL operations that I've been invoking are actually extension methods on the client, so those have to be imported as well. Usually the IDE gracefully handles that for you, but occasionally if you see red squigglies when you're using the DSL notation, that means that there's some missing import that you'll need to pull in. The request objects and actually the response objects and all of the intermediate data types that are used by them are in a model subpackage. Those will have to be imported as well. Usually the IDE will handle that for you. And then some of the common types that are used across the SDK that are not specific to any given service are in a Smithy namespace or another high-level SDK namespace without the services component. All right, now we've talked about making some basic calls. Let's talk a little bit about asynchronous calls. So all of the operations that we've been performing so far have been synchronous. Let's set up a call where we invoke 2 operations on 2 different services and print out the result of both of the operations. And let's actually measure the time it takes to do both these operations individually. Okay, let's run this and see how long it takes. All right, so fetching S3 buckets took about half a second. Fetching the DynamoDB tables took about a quarter of a second. All told, both operations took about 3/4 of a second, which is roughly, roughly those 2 numbers added together. Any extra is probably things like me printing out to the console, taking a little bit of extra time. But as I mentioned in one of the slides, we set this up to be coroutines friendly. All of the operations that you can invoke on AWS services are suspend methods, and the IDE even highlights them over here in the gutter with this little squiggly line and a suspend function call annotation. So we can make this asynchronous. And then, of course, we have to await on the result. But this should make our code run a little bit faster. Cool. So now the amount of time that it took is no longer the sum of the 2 times for each of the operations. It's a lot closer to just the larger of the 2 operations, in this case, still fetching the S3 buckets. So this is an example of kind of, oops, sorry, my mouse. This is an example of some static asynchronous calls. Let's take a look at some more dynamic asynchronous calls. For this example, let's assume that we've got a list of files that we want to upload from a local directory. For each of these files, we want to call S3 put object. Put it in a specific subfolder in S3. And again, pass the streaming byte body. We'll print out a debug message here. All right, Let's see how long it takes to upload my directory full of files. So you can see it progressing alphabetically through a list of files, in this case, pictures of animals. It's proceeding relatively slowly because my for each loop doesn't really know what can be parallelized, and it's waiting for each put object call to finish before invoking the next one. All told, it took about 17 seconds, and I bet we can make it faster by, there we go. I bet we can make it faster by turning these into async calls. So first we'll have to turn our for each into a map, wrap these calls in async, and then on the result of this map, which is going to be a collection of deferred results, we'll await all of them. Now when we run this, you can see that they're uploading much faster in a slightly non-deterministic order, and instead of the previous 17 seconds, it takes only a little over 2 seconds to finish. Using dynamic asynchrony in the AWS SDK for Kotlin is great. You may occasionally run into issues where there are so many tasks to run that you may find yourself running out of resources or running out of coroutines to actually execute these. Sometimes that may involve kind of right-sizing your coroutine dispatcher or adding semaphores to make sure you don't run too much work at once. But by and large, it's pretty easy to turn synchronous code into asynchronous code thanks to Kotlin's like coroutine support. All right, next let's take a look at pagination. So many AWS operations that return more than one entity, or that can return more than one entity, like the list tables, list buckets, list objects that we've seen so far, support pagination. But they do it in a way that's not always the most straightforward when you first see it. DynamoDB's scan operation looks at a table and returns the items that it finds inside the table. So let's take a look at a dictionary table that I've created. Helps to get the parameter name right. There we go. Oops, not count. How about size? Size is better. All right, let's run the scan operation on my table and see what happens. Let me stretch the window a little bit here so we can see all of it. So my dictionary table contains a list of every English word known to man, I think. And there's well over 400,000 of them. So I know that just from the size of results that were returned that it didn't return everything. Moreover, I know that the table is sorted, and the very first word begins with A, and the very last word ends with or begins with Z. And so I can see from the first and last values that we got that I didn't get all the items in my table in one call. Items or operations that are paginated have a special value on the response. It's named differently sometimes, but in this case, for DynamoDB, it's called last evaluated key. This last evaluated key indicates where DynamoDB stopped scanning and said, I've got enough information, I'm going to send you what I've got right now. If you need more, call me back later. The way that you would do that, if you were to do it manually, is by adding an exclusive start key to the next invocation of the scan operation. In this way, you can imagine that you might write a loop that might get a first page of results and then pass that last evaluated key to the next call, and then pass the next last evaluated key to the next call, and so on and so forth. Fortunately, the AWS SDK for Kotlin has a built-in method to handle that for you. And it's called scan paginated. Now the thing that I get back from this method invocation is no longer a single scan response. It's actually a flow of scan responses. Flows are Kotlin coroutine's asynchronous data source or asynchronous collection type, which allows us to kind of lazily enumerate over the responses as we need them. So in order to perform any operation on them, like collecting them, we will do the following. Put my print line statement in here as well. There. Now this code should iterate over each page in sequence until there are no more pages left to find, and print out some summary statistics about each one. So here it is, printing until it runs out of pages. There's about a dozen pages, and we can see that the very last page ends with a word that starts with Z. I don't even know what this word is, honestly, but it's the last word in the dictionary. All right, so scanning over pages is great, but pages are not often the thing that we care most about when we have a large data set. The pages are really just the bounds of what could be encompassed in a single response, and usually it's the items themselves, not the pages, that are most interesting. So the response also contains an items flow, which turns our flow of scan responses into a flow of actual DynamoDB items. DynamoDB items are maps of attribute names to attribute values. So let's see what we can do with those. So here's some code to find every item in the table, print it out to the console in a short and easy to digest format. When I run this code, you can see that big blocks of words are printed all at once, and there's a small delay as the SDK goes back to Dynamo and fetches the next page. But eventually we make it to the end of our list, and we've printed out every single item in the table. I highly recommend that when you're dealing with APIs that return multiple pages of data, that you use one of the paginators, that you don't write your own pagination. It can be done. There's definitely ways to do it. But it's far more foolproof to use one of the built-in paginators. One more note about paginated APIs is that most of them in their documentation indicate that they are paginated and what the pagination kind of like limit is. So if I take a look at the DDB scan operation and the documentation that's available for it in the SDK, you can see that it mentions that it stops after 1 megabyte. So once it accumulates a megabyte worth of data, it stops looking for more, sends that, and this next page will have up to a megabyte of data as well. Some APIs return pages based on the size of data, others return pages based on the number of items in the response. It varies, but the documentation will help you figure out which is which. All right. Last code example I wanted to cover is waiters. So some operations that you invoke against AWS services are asynchronous. They're all asynchronous from a Kotlin standpoint, but even from an API invocation standpoint, sometimes AWS will get back to you immediately and say, yes, I've heard your request, I'll get to it in the background. An example of one of those kind of operations is creating a table in DynamoDB. Creating a table has lots of arguments, so I'm going to take a shortcut here and paste in some code that I did before. So because I know the create table operation is asynchronous, and I know that it takes roughly 5 to 10, maybe 20 seconds to actually fully provision a table and make it available for use, I'm pretty sure that if I tried to immediately turn around and put an item into this table, that it would fail. Oops. Oh, and I have to spell value correctly. There we go. All right, so let's see what happens when I run this code. Okay, My create table API said it was successful, or at least it didn't throw any exceptions, but immediately as soon as I tried to put an item in there, I got this resource not found exception, and the resource that it can't find is the table. It's still being created asynchronously. If you write code like this, you could do something like insert a manual delay. You could poll AWS repeatedly to find out if the object that you're waiting for exists, but there's a primitive built into the AWS SDKs to do that for you, and those are waiters. All right, so I've got my create table API call, I've got my waiter, and I've got my put item call. Let's see if this is enough to sequence things in the correct order. Oops, this is going to fail. Resource and use exception means that I'm trying to create a table that already exists. Because my create table operation is asynchronous, and because the API call succeeded, that means that AWS began creating the table in the background, and by now it's finished. So trying to create another table again with the same name is of course going to fail. Let me update this table name constant to something different and try again with a brand new table. Okay, so my create table API returns almost immediately. Now my waiter has been invoked. And what it does is it immediately pulls AWS and says, does the table exist? No, I'm going to back off and try again, back off and try again until I get a successful response. And then when it's done, control resumes and the item gets inserted after that. All right, this is the last kind of code example I wanted to cover, so let's switch back to the slides for a couple of closing thoughts. Future plans. So right now, the AWS SDK for Kotlin is in developer preview. Its version numbers are less than 1.0. You saw in my Gradle configuration, it's something like 0.21.4 right now. What that means is that we're still finishing up various features for some niche use cases. We're making some API improvements to make sure it's as easy and idiomatic to use as possible, and we're doing some performance optimizations to make sure it runs as well as possible in a bunch of different environments. While it's in developer preview, we are kind of acknowledging that we may have to make backwards incompatible changes to the API in various areas. That means that code that you write against the Kotlin SDK today may or may not work against future versions of the Kotlin SDK until we get to a stage of general availability, or 1.0. Once we get to that point, then we'll have stronger guarantees about API stability from version to version, and you'll have confidence that the code you write once can continue to work as you upgrade to newer versions. After we go to general availability, our next big task is going to be to add support for additional KMP platforms. So as I mentioned, JVM is what we support today. We want to take a look at native next, possibly JavaScript for the server side after that, and additional KMP platforms as they stabilize and become mature. Additionally, we want to add support for some higher level libraries. A lot of AWS SDKs have a notion of an S3 transfer manager, which kind of simplifies transferring large amounts of objects in and out of S3. Imagine that simple asynchronous example that I wrote, but kind of on steroids. Additionally, some SDKs have a concept of a DynamoDB mapper, which makes it easier to access items in DynamoDB tables in a more object-oriented format, rather than some of the attribute values and array indexing that I was showing earlier. In order to help shape our future plans, we want to hear from you guys. So come to our GitHub repo, file us an issue or start a discussion, and take our Kotlin developer survey where we try to get some insight into how you guys are writing code right now, what kinds of environments and platforms are important to you, and how we can best support them with an AWS SDK. Thank you. Don't forget to vote, and I'll open it up to any questions you guys have.
Yes, thank you for the talk. And you said you built Kotlin SDK from scratch. So does it mean you're going to maintain and update both Java SDK and Kotlin SDK in future? And why you prefer this approach with two SDKs over one with SDK written in Kotlin but support Java compatibility? And also in this case, if you have two independent SDK, in case if I have application where part of code is written in Java and part of code is written in Kotlin, what should I choose?
Which should you choose? No, those are all great questions. So yes, there will be an AWS SDK for Java and an AWS SDK for Kotlin going forward. They'll continue to be built independently and to support as best they can the Java ecosystem and the Kotlin ecosystem, which may mean making different choices as far as API design or the features that they support. The reason that we chose to not reuse the Java SDK is for the reasons that I mentioned on one of those early slides. We wanted it to be as idiomatic as possible for Kotlin developers. We wanted to be able to support multi-platform, which Java doesn't have a great answer for today. We wanted coroutine support. But more importantly, we recognize that a lot of developers are choosing Kotlin over Java for specific reasons, like the code is just more pleasant to write. The standard library has, interesting things that you can do with it that aren't yet available in Java standard library. So for that reason, we want to offer SDKs in the languages that make sense for individual developers. Sometimes that's going to be Java, especially in a lot of legacy cases, that's going to be Java. For a lot of newer applications or a lot of mobile applications, that's going to be Kotlin. I think you asked a question as well about if you have some code that's both Java and Kotlin, what should you do? How should you access an AWS SDK? Right now, the only straightforward answer to that would be to use two SDKs in your code, have two dependencies for accessing them, which is not ideal, or to use the Java SDK if you are only targeting the JVM platform. Right now, it's not super easy to call the Kotlin SDK from Java code. That's something that's in our backlog to take a look at and see if there are ways we can make it easier for Java developers to call into the Kotlin SDK. That's not something we've prioritized yet since we're a Kotlin first SDK. Yeah.
Thank you very much for your talk. I have a quick question, possibly the one. You demoed both S3 and Dynamo, and S3 had synchronous APIs, while Dynamo, well, at least the creation one, was asynchronous. Why did you decide for this one to be asynchronous instead of making it synchronous and let the developers choose to use coroutines or have it synchronous?
Yeah, so the question of whether a particular operation is synchronous or asynchronous exists outside of any particular SDK. So the create table operation is asynchronous for the Java SDK, for the Python SDK, for any other SDK that calls it. Kotlin the Kotlin SDK tries to mask some of the complexities of dealing with asynchrony because we have coroutine support and Kotlin developers are used to kind of thinking in a more asynchronous mindset by default. But individual AWS services are the ones decide which operations should be synchronous and asynchronous. I don't work on the DynamoDB team, so I don't know for sure why they chose to make create table asynchronous, but if I had to guess, it's because the table has to be allocated in a potentially very expensive way. It has to be sharded across multiple different availability zones, and it has to be highly available and have enough throughput to be able to support requests. So because that takes a while, like I said, maybe 5 to 10 seconds, they figured that it was probably better to return an API response as soon as it's validated all the input parameters and made sure that it can create the table, and then allow the table creation to happen in the background. That's my guess. Yeah. No more? All right. Well, thanks again, everyone. I really appreciate you coming out. Hope to talk to you all soon.